So welcome back from coffee. So the slides will be available in our website. We will post them today. And if you take pictures and post them in your social media, please use our hashtag Paraty, such that you can follow and grab the pictures that you take. And the courses will be available later in our YouTube channel, so please also follow our channel. We will. So we'll start our next course, which will be given by Steve Walborn and Esteban Sepúlveda. The course está aqui, Steve, o seu. Posso? Yeah, okay. So Steve is a professor in University of Concepción, and Esteban also is a professor in University of Concepción. They will give this course together. So this first lecture will be given by Steve. Steve was my advisor in my PhD in Rio de Janeiro, so I know him from 15 years. Yeah. He's a big friend of mine, also was my advisor in PhD. And then we'll talk about the next generation fiber optics, which they study in Concepción, which are very intricate fibers. So Steve, welcome. Thank you very much for being here with us. You have one?
Hello? Can you hear me? Is it okay if I stay down here? You can see me? Okay. To be honest, I'm afraid of falling off the stage. Okay, so I'm Steve. As Daniel said, Esteban and I will be dividing this course, and there's the title. So to start, I just want to say it's great to be here in Paraty. I've been to every Paraty event except for one. So I'm one of the people in the little 2007 bar in the graphic that Daniel showed. Yeah, so I've been every year, and it's, so I saw from the statistics that a lot of you are here for the first time. So I encourage you to take advantage, to enjoy yourselves, and to take advantage to get to know your colleagues. These will be the relationships that you build, and will be the basis of collaborations in your career. Many say scientific friends that I have, I met in Paraty years ago, and we collaborate together, and it's very still today. And it's very fun when you get to meet at conferences and so on throughout the world. So yeah, so enjoy yourselves. Also, I want to say thank you to the organizers. I think maybe we can all give them some applause. So I was one of the organizers in 2007 and 2009, and it kind of looks really easy. They make it look easy. Let's put it that way. So it's not easy. It's very difficult. The funding is difficult. It's difficult to get everybody here. It's difficult to reserve the venue. All this work that goes on behind the scenes, months or even a year before the event and during the event. It's a big task. So they deserve all the appreciation. Okay, so during the talk today, this talk, and then I guess our second class is on Thursday and the third on Friday. Please ask questions. Stop me if you wish. I'm a native English speaker, so if I start to speak too quickly, slow me down. I'll do that if I get excited about things, and I'm very excited about the work the stuff I'm going to present to you. So yeah, just let me know. And yeah, so have a good time here this week, and if you're staying around for next week. So yeah. Okay, so before I just get into the course, I just wanted to tell you a little bit about me. So I originally did I'm from the United States originally. I did my bachelor's degree in physics there back in the late 1990s. Then I moved to Brazil, and I went there to do a master's degree. and I stayed to do a PhD. And actually, that's when I met Daniel Tasca, and also Rafael Chaves, and Naj, and many other people around that time in Belo Horizonte, both Marcelos. Yeah, so Danielle and I actually, when I was just starting my PhD and Danielle was an undergrad, we did a project together in Carlos Smoking's lab in UFMG. The first experiment I ever did was in collaboration with Marcelo Daniel Cunha, who's circulating the auditorium in the back there. Yeah, so there was a kind of a great thing to do, going to Brazil and being in Belo Horizonte. After that, I went to Rio as a postdoc at the Federal University of Rio de Janeiro. Then I became a professor there until 2019. In 2019, I moved to the University of Concepción in Chile, where I live today. In Concepción, so there was already a quantum optics, quantum information group there in both theory and experiment. In terms of experiment, we'd say the group was kind of founded or really given a lot of momentum when Gustavo Lima went there in 2006 or 7, I believe, as a postdoc, and then got hired as full-time professor and so on. And Gustavo, he and I met also in Belo Horizonte, where we were kind of master's students at the same time, and then PhD students at the same time in neighboring laboratories. So he started the group. Esteban was a student of Gustavo's, and then was also hired as full-time faculty. And then I arrived in 2019 on the experimental side. And then Professor Aldo Galdo has a theory group that, of course, we collaborate together. There's also Carlos Saavedra, but currently he's the dean of the university, so he doesn't have very much time for research. But he also is really key to just getting this momentum going in Concepción. And then also there's some other experimentalists in quantum optics and related things at some other universities in the city. So in Concepción there's, I don't know, Stephen will tell me the exact number, but at least 5 universities. It's like in the south of Chile, and it's the largest city in the south, and so a lot of the students from the south of Chile come to Concepción to do university. So I don't think it has to be said, we're always looking for collaborations. And so an interesting thing we have in Chile is this Millennium Institute for Research in Optics, MIRO, which is the perfect name for an optics institute if you're a Spanish speaker. And so yeah, here's the website there. So that's kind of a really important thing for us because it gives us some funding that is like some predictable funding. So you can arrange for postdoc positions and things like this, ahead of time. And so, so this is kind of really important to do research, to be able to hire people and plan ahead. Okay, so now let's get into the course. Esteban and I divided the course into 3 classes. Well, we didn't do that, we were told we had 3 classes. So the way we split up the topic is this. So class 1 will be today. We'll talk about encoding quantum information and light, and then more specifically talk about optical fibers and space division multiplexing, which is a kind of, near commercial technology that we're trying to exploit in our lab, and then show how to kind of put these things together and do some interesting photonic quantum information things with this kind of new developing technology. And then class 2, we'll talk about more applications and getting into some, even more interesting things. And in class 3, we'll talk about this type of space division multiplexing technology with entanglement. Okay, so that's the plan. We'll see how it goes. Okay, so why are we interested in photons? Well, there's many reasons. One of them is that I think everyone agrees that photons, or light in some form or another, will play a part in quantum information because that's how you're going to transfer quantum information one place to another, right? By sending photons, like flying qubits, if you want to call them that. You can do this with the losses in free space and optical fibers and so on. So it's quite interesting for that. So they're going to be a key component in kind of whatever you want to do. Of course, in terms of communication, but also even in say short haul kind of scenarios. If you want to go from one, say, quantum server to another over a meter or whatever, you probably need to use light. It's also quite interesting because there's many different degrees of freedom that you can choose to encode the information in the light. So that's something we're going to talk about quite a bit today. And another nice thing is you can even encode higher dimensional systems, so not just qubits, but qubits or whatever qubits, however you want to define it. In qubits for dimension 3, qubit quartz, dimension 4, and MIRO. And of course, like, why do you want to encode higher dimensional information? Well, I mean, of course, if you can put more information in a single photon and send it from one place to another, you send more information. But there's also some quantum information tasks that are not just, do not just benefit from having more information there, right? But also it's essential. Like, for example, in quantum contextuality, you cannot show quantum contextuality with qubits. In the large dimensional systems, and you can ask Marcelo about that for more details, right? So, I mean, given these sort of considerations, so we want to use light, and so of course we want to take advantage of everything, of all the available technology, right? So you have telecommunications. I mean, we have these huge demand to send data around the world in optical fibers. So of course we want to take advantage of all this technology that's being developed all the time, right? In terms of fibers or say different types of photonic chips or whatever. So if you work with light, you want to use what's available and follow the trends in the field, right? I should just mention, like, there's another reason why, I mean, in say, South America, a lot of the laboratories work with light because it's a lot cheaper, right, compared to other systems. I mean, just if you want to set up, a functioning quantum optics laboratory doing, say, nice, meaningful experiments, you need maybe a few $100,000 to do something like in atomic physics. You're talking probably at least an order of magnitude more money. So, I mean, for that reason, I think there's a lot of quantum optics laboratories in South America and other places in the world. Okay. So how can you encode information into light? So just in general, like when you want to consider how am I going to encode quantum information in any system, well, you want to be able to prepare some kind of quantum state. You want to be able to perform some sort of operations on it with some sort of devices, whatever they are, and then you want to perform some sort of measurements on those states. So when you're kind of considering how am I going to put information in these photons, you want to think, how can I do kind of these 3 steps? So I'll just show you some of the possibilities, and then I'll show the kind of one we're going to choose to work with in these optical fibers. So I think Nadja, in her talk early this morning, mentioned the polarization as qubits. So this is kind of a more simple and really kind of beautiful way to encode a qubit into a photon is use the polarization of the photon, right? The photon is a quanta of light, and so we can, let's just for the sake of this today and the rest of the week, we can just think of, in this context, the photon as though it was some sort of particle, right, that has certain properties, and one of the properties it has is the polarization. We could make maybe more more correct kind of image, defining modes and populating these modes with photons, but just for this, to keep things simple, the photon, we're going to talk about the polarization as though it's a property of the photon. So, so you can define a computational basis using, say, the horizontal and vertical polarizations. It's a 2-dimensional system. You can manipulate the polarization using wave plates, which will rotate the polarization and change it in different ways. And you can, with a certain sequence of wave plates, you can implement any unitary transformation on the polarization. It's quite easy. You can buy these in a catalog, and they're very high quality, and that's everything's wonderful. To do measurements, you can use polarizers or polarizing beam splitters, also really high quality. You buy them online with your credit card, and no problem. If you want to, in terms of transmission, in free space, the air is not birefringent, so the polarization pretty much, a photon does not depolarize or anything that travels through free space, so it's pretty good. In optical fiber, it's a little tricky because the fiber can be birefringent, so that means the polarization is going to be changing as the photon propagates. But you can also just kind of monitor this, and you can correct this if you're monitoring this in real time. Let me just ask a question. Can everyone read what's written on the bottom part of the slide? If everyone got to it? Okay, just if as a mental note for next class, I'll pull everything up with it.
Just to confirm, a little tricky for optical fiber using birefringent dispersion method.
No, yeah, so it says, a little tricky for optical fiber use because of birefringence and dispersion and so on. So, yeah. Okay, so another way to encode information are using what are known as transverse spatial modes. So these are kind of so what's shown here on the figure is, so imagine that you have a laser beam coming out of the screen, and so you can, this laser is producing, say, some sort of cavity or so on, and this cavity has certain, say, normal modes, right? And so these are the normal modes in say, the cylindrical basis. If you go to the Cartesian basis, you have, say, these normal modes, and so you all recognize in the top left of both figures a kind of Gaussian-looking mode, and then you go to kind of the higher-order modes of, say, a laser cavity. And so you can, prepare photons with a cavity like this and produce a single photon that has this as its spatial mode, or a single photon in this spatial mode. Yeah, so this is really standard in optics, and there are some techniques you can use to do different transformations between the modes, so the holograms, or as I mentioned, cavities, or different sets of lenses and so on. So this is, a fine system to use for sending information. In Brazil, for example, several groups use this, and of course, you see already here now we don't have just two, say, basis states, but we have, as kind of, these are in principle infinite dimensional systems, so we can kind of encode as much information as we can, right, as we want. And so just in the context of later when we talk about optical fibers, so some of these modes do appear in optical fibers as well, or modes that are, say, kind of analogous to this when you solve the wave equation inside of the fiber. Another type of encoding is, say, using temporal modes. So here, if I have, say, two pulses really close together, or if I create a photon somehow that can be in two, say, temporal modes, say, time slots. So I can have a photon in, say, the first time slot here at time equal to 0, or I can delay it and put it in time slot, say, that's delayed by some time delta. This is quite a good scheme to use in fibers because of mode dispersion and so on. The modes will just kind of disperse equally and everything. You can also construct some devices. It's slightly more complicated, but you can construct some devices to prepare, say, arbitrary superposition states of these two time slots, or you can construct some sort of device using some optical components to measure superposition states and so on. So this is also quite a good system. So finally, I'm going to talk about what will be kind of the basis of the course today and the rest of the week is using momentum encoding. So here, this is kind of what's sometimes called dual rail encoding. So imagine, say, two momentum modes. So these are just like kind of plane wave vectors, if you will. And so this little circle here represents my photon. So the photon can either be in the upper mode or the lower mode. And so if it's in the upper mode, I call it state 0. If it's in the lower mode, I'll call it state 1. And so I have my qubit, my computational basis defined as such. So the interesting thing here is that it's quite easy to do operations, right? So if I were to try, say, some sort of phase gate on this qubit, I can put a piece of glass or some sort of optical element here that applies a phase only to the lower rail, the lower mode. so that if the photon is in the upper mode, of course the photon's not even going to see the glass plate, so nothing happens to the zero state. Whereas if the photon's in the lower mode, it will feel the presence of the glass plate, and the one state will thus acquire the phase. So this is quite easy to do in principle. And the other element that is interesting here is a beam splitter. So if I take a beam splitter, which is kind of a cube here with certain transmission and reflection properties, transmission and reflection coefficients given by T and R here. And so basically, if the photon enters here in this horizontal mode, it has a probability of T of transmitting through the beam splitter, or a probability R of reflecting through the beam splitter. And for the blue mode here, it's the opposite. So with this, you can, if you come in with a zero state here and say the blue mode, or sorry, the red mode, I create a superposition between the 0 and 1 with weights which are given by these numbers here. So with this, you can create superposition states.
And we have the opportunity to see an experimental using a theoretician beam
splitter. Yeah. Thank you, Marcelo. With this, so this is quite nice because with these two kind of elements, you can actually construct anything you want. And not just in dimension 2, but in dimension D. So this is a figure which I took from this paper by Clemens, 2016. And so what this is showing here are kind of two schemes. One by Clemens, but a previous scheme by Reck et al. In 1994. And what they showed is that if you take, so imagine you have, say, D input modes and D output modes, and you want to construct some arbitrary unitary operation among these modes. You can do this using this arrangement of beam splitters and phase shifters. And so what these diagrams here are showing is the following. Each point where two lines cross, it actually represents an interferometer, right? And so an interferometer is constructed by two 50-50 beam splitters, right? So light that would come in, say, the upper mode here, would first go through a phase shifter, then go through a 50-50 beam splitter. So half of the light would split to the upper mode, half would go to the lower mode. In the upper mode, there's another phase shifter with a different angle. Then those two components meet at the second 50-50 beam splitter and split. So this kind of basic element here is what's represented by this intersection here. So if you take this kind of basic building block, you can arrange it in different structures, and you can prove that with this kind of structure you can reproduce any arbitrary, any unitary operation. Of course, when this is quite interesting from an experimental point of view because the beam splitters are all 50-50 beam splitters, so it's static in that regard. And the only thing you have to do is change the phases. So if you have, say, electro-optical phase modulators, you can build a device where you're sending electronic signals, changing the phase, and changing the unitary however you like, in principle. And so when you do the kind of accounting here, you see that, well, in both schemes you need something like D squared by 2 beam splitters. And so the only difference really between these two configurations is that this one by Clemens in 2016 has a shorter optical depth, which means that in principle you have lower losses on average because the longest path between the device is shorter than the longest path in the upper device. So it has an advantage, but conceptually they're both more or less the same. So this is quite nice because you have this kind of basic building blocks that are optical elements which exist in the lab in several different forms, right? Beam splitters and phase shifters. We have those, and you can so you can use them to build anything you want. Okay, so with all these different degrees of freedom, you can, of course, you're not restricted to just using one or the other. You can kind of use them all together in some way, whatever is advantageous to you. I mentioned the temporal degree of freedom, but you could also encode in different frequency modes and so on. It's more or less similar to what we're describing. And so you can use them in conjunction with one another, or you can also transfer, say, information from one degree of freedom to the other, essentially deterministically in principle and quite easily. So, I mean, a polarizing beam splitter will transfer polarization information to the spatial mode and vice versa. So, with some wave plates, so you don't really have to worry so much about, oh, I coded information in the polarization and now I can't get it, but I want to put it in spatial mode, you can just transfer it over. It's not a problem. So you see that, so polarization is a two-dimensional system. All the others are, larger dimensional systems, and of course, altogether, you can, in principle, encode, as much information as you want, right? So this kind of gives you the question, like, well, why don't I just use a single photon in some gigantic, interferometer or whatever, and build a, say, a quantum computer? If I can do a D by D unitary, I can just make a gigantic quantum computer, right? Of course, the answer is that this isn't scalable. So if I want to say represent n qubits, I need 2 to the n modes. So of course, it's exponential growth in terms of the number of modes needed to encode a certain number of qubits. And so if you just think about like a fun little calculation, think about an interferometer. So I have some momentum modes. I'm going to choose 2 to the n of them. And let's say like a kind of a modest number of qubits, like I think I chose 40. So if I suppose that the momentum modes can be, say, one wavelength apart, that would kind of be the minimum distance they would have to be apart. The width of this interferometer is going to be something like 2 to the n times the wavelength in width. So for 40 qubits, that would mean my interferometer is 1,000 kilometers wide. So you see that this kind of idea quickly goes south. However, I mean, there is some advantage to using high-dimensional systems, and I know this is, I've like worked in kind of this sort of topic for say 20 years, and I like to think about these things. So there's another issue, which is say the detectors and detector efficiency. And so if you buy equipment for your laboratory, you quickly see that detectors are the most important, one of the most expensive components, right? So, of course, if I want to work in high dimension, if I want 40 qubits, and I'm going to use, say, 40 photons, if photons are cheap, so I might as well use photons to encode information, and so if it's qubits, I need, say, 2 detectors, one to see the 0 state, one to see the 1 state, so I need something like 80 detectors, say, to detect those 40 qubits. However, when I use high dimensions, again, the same kind of exponential scaling means I need more than 1 trillion detectors. So, in terms of the high dimensions, not just, of course, no one's gonna, maybe you said, well, 1,000 kilometer wide interferometer won't do, but I could maybe have a kilometer. But even if you reduce the number of qubits to something a lot more modest, the detector issue is of course immediately, out of your budget. So that's another problem in terms of like using high dimensions. But on the other hand, the detectors are not perfect efficiency. So, and also the system always has losses in it, right? So if you do the scheme of, say, encoding n qubits and n photons, the efficiency, the overall detection efficiency to see those n photons is going to be the efficiency of a single detector to the n, assuming they're all equal. Whereas for a single photon, kind of n qubits in a single photon, it's going to just be an efficiency n, or eta, sorry. To detect all the information, right? So there is kind of some advantage of using, say, putting more information in a single photon, but you have to kind of, you can't get carried away. So the thing I always like to think about is there's definitely an advantage, but you want to keep a dimension where, let's say, not much larger than 2. So the 3, 4, 6, 8, whatever you want. There's some upper limit, which is, say, like around the order of 10, I would say. That could, of course, change if you have more funding, or maybe you have some, there are nowadays cameras that can see a single photon, which might have, thousands of pixels or tens of thousands of pixels, and maybe you have one of those and can use it well. So it might not be an issue, but there's definitely an upper limit, right? So all this is just to say that, when we hear people talking about high-dimensional encoding, it's definitely interesting, and it's something that we do a lot in our lab. But in order to do, say, large-scale quantum information processing with photons, you need, of course, multiple photons. And that's a technical challenge. I mean, not just because of the efficiency issue, but of course, how can you produce, I mean, with the sources, how can you produce n photons all at the same time in your system and measure them and so on. Yeah. Okay, so, so this is what we're working with. So what I want to switch topics a little bit now and talk about the optical fiber technology, which we're going to use to work with these photons. So, let's see. So as you know, optical fibers are, say, a piece of material that actually where, let's say, a piece of glass, where in the middle you have, let's say, a core region where the index of refraction is larger than an outer region known as the cladding. So this is like a cross-section of the fiber. And from just like, say, a geometric optics picture, light rays coming into the fiber. If the angle of these rays is smaller, say within like the acceptance angles of the fiber, the light will remain trapped within the fiber due to internal reflection. So I don't think we have to talk too much about that, but that's the general principle. So if you kind of ignore losses, this light will propagate all through the fiber, and that's it. Right? So from a wave optics perspective, you solve the wave equation inside of the fiber, and so there are fibers that are known as single mode fibers. So basically, that means that kind of bundle of optical rays which propagate through the fiber are formed what's like the fundamental mode of the fiber, which is something like a Gaussian profile. You can also have multi-mode fibers.